So a different comparison test is called the limit comparison test, which is also another test for absolute convergence. A little bit more restrictive, though. So we've been saying for absolute convergence, we could still have terms that are zero. They just could be positive or zero. They just couldn't be negative. For a limit comparison test, I'm not allowed to have any terms that are zero because of how we're approaching this. So I have to have all positive terms. I'm going to, like the direct comparison test, compare the series I'm looking at to a second series, which must also have all positive terms. None can be zero. I really, really like this test personally because whereas the ratio test is great for exponentials and factorials, it's not good with rationals. The limit comparison test is really, really nice with rational functions because the second series we're going to compare our original series to is usually going to be the end behavior model for the original series terms. So what I'm going to be doing is I'm going to be comparing the original series to the second series, and it has to be in that order. So if we're thinking in terms of a fraction format for our ratio, original series must be on top, comparison series has to be on the bottom. If I do the limit as n goes to infinity of that compare original to comparison series, and I get a positive constant, then either they both converge or they both diverge. If I get 0 for that limit and the comparison series converges, then the original must also converge. And if I get infinity, if the comparison series diverges, then the original also diverges. The second two parts for that are actually the direct comparison test. Because if this limit is approaching 0, then that means b of n is bigger. And if the bigger series converges, the smaller series must also converge. And then if my limit is infinity, that means that a of n is bigger than the b of n. So if b of n is diverging and a of n is bigger, then a of n also has to diverge. I will admit I tend not, if I get either of the last two results, I typically will go to a different test, like the integral test, which is a later video. But if I really like this for rational functions as long as I get a positive constant, not 0 or infinity. Please note, I've dropped the absolute values in this because a sub n and b sub n have to be positive already. If you put the absolute values, and you'll see in the examples, sometimes I do, sometimes I don't. It's perfectly correct to still put the absolute values to make them be positive, which is a good habit to actually be in. So an example of this. The 2n plus 1 over n plus 1 squared is my original series, where n's going from 0 to infinity for the summation. B sub n is going to be the n behavior model of that. So on top, 2n is taking over. On bottom, if I expanded n plus 1 squared, n squared would take over. And I get 2 over n. I can already tell that 2 over n is a p-series. I have a constant on top. So sum from 1 to infinity of 2 over n is a p-series, where p equals 1. 1 is not bigger than 1, so that would diverge by the p-series test. But I can do my limit to compare as n goes to infinity. I'll put the absolute values here of my original 2n plus 1 over n plus 1 squared compared to the 2 over n. So I'm going to do some simplifying here. So 2n plus 1 over n plus 1 squared times n over 2, which is the limit as n goes to infinity of 2n squared plus n over 2n squared plus 4n plus 2. Because n is going to infinity, I could do L'Hopital's rule because the top is going towards infinity and the bottom is going towards infinity. But I can also use an n behavior model to evaluate this limit. So this is the same as the limit as n goes to infinity of 2n squared over 2n squared, which is 1. Because this is a positive constant, both series either converge or both series diverge. Helps if I can spell diverge correctly. I already said over here, that series diverged. So that means my original series, where n is going from 0 to infinity of 2n plus 1 over n plus 1 squared, also diverges. And that would be by the limit comparison test.